It's time to get things moving. On my robot I have 4 brushed DC motors, which rotates the wheels and in turn makes the robot move. Brushed DC motors are easy to control. The speed and torque is proportional to the applied voltage, so you vary the speed and torque by varying the voltage. But the motors can't be directly connected to the pins on a microcontroller because they draw quite a bit of current, more than a GPIO pin can supply, so you need a motor driver. On my robot I have 2 motor drivers, one for the motors on the left and another for the ones on the right. I get away with only having 2 motor drivers since I do skid steering, meaning the motors on either side always drive in the same direction with the same speed. These motor drivers essentially take 4 inputs, one that connects to the power supply, a battery in this case, and 3 that connects to the microcontroller. 2 of which control the drive direction, whether the motors are rotating in clockwise direction, counterclockwise, or are stopped. These are just digital, low and high, and then the third one controls the speed via pulse width modulation, PWM. Pulse width modulation is a method which involves toggling a pin on and off at a certain ratio, so-called duty cycle, to effectively vary the average voltage. For example, if we have a signal at 7.4 volts when active and we have a duty cycle of 70%, the signal will be active 70% of the time, yielding an average voltage of 5.2 volts. So by varying the duty cycle between 0 and 100, we can vary the output voltage between 0 and 7.4 in this case. PWM is commonly used for controlling brushed DC motors, but it's also used for other things such as controlling the light intensity of an LED. As for this video, I'm going to write code to control the motor drivers I have from my microcontroller, and I'm going to separate the code into 3 abstraction layers. At the bottom, I'm going to implement a PWM driver, which is going to use the timer peripheral of my microcontroller to emulate hardware PWM, since my microcontroller doesn't have any dedicated peripheral for PWM. And above that, I'm going to have a layer for the motor driver, which is going to depend on the PWM driver, but it's also going to control the other pins of the motor driver. And thirdly, I'm going to have a layer on top to simplify the drive interface for the application code. Similar to my other videos, I'm using the development board for demonstration, and for this video I created a simple motor driver circuit including 1 motor driver and a DC motor. This circuit won't obviously test the full functionality since my actual robot has 2 motor drivers and 4 motors, but it will provide some reassurance until I move on to the actual robot, which I'm going to do later on in this video series. Okay, so I'm going to start by implementing the code for the PWM driver, which is going to be this part of the software architecture. And in this video, I'm not going to create a new project from scratch in the IDE, and instead I'm going to add the code directly to the rest of the project code. And this means that if you haven't watched my previous videos, there will be some unfamiliar code, but I think you will be able to understand what I'm doing here anyway. And if there is anything that's unclear, you can just watch the previous videos or read the code on GitHub. And the reason I'm doing this is because it's getting a bit too much implementing things from scratch, separate from the rest of the project code, and then move the code into my project afterwards. So for the PWM driver, I'm going to have 2 files under the drivers directory, 1 header file and 1 implementation file, the way I usually structure my drivers. So I'm just going to create 2 new files, and I'm also going to add the implementation file to my make file. And then starting with the header file, the interface is going to be pretty simple. I'm just going to have 2 functions here, 1 function to initialize the driver and another function to set the duty cycle, which is going to take 2 arguments, the first of which is going to be the channel, and then the second one is going to be the duty cycle in percent, so from 0 to 100. And then I have to also define the enum for this. And in my driver, I'm just going to have 2 PWM channels, because I'm going to have 1 PWM to each motor driver, and I have 2 motor drivers connected to 4 motors. And then I can add a comment on top as well. And jumping over to the implementation file, I can start by including the header I just created, and then also just create the bodies for the 2 functions. And as I usually do, I'm going to make sure that I don't call this initialization function multiple times. So I'm going to have a bool, keep track of that, and then assert in case it's already initialized. And I also need to include std int here. And then, as I said, since my microcontroller doesn't have any dedicated peripheral for pulse width modulation, I'm going to achieve the same behavior by using the timer peripheral. And my microcontroller has two timer peripherals. And since I've already used one of them for the IO remote functionality, which I implemented in the last video, I'm going to use the second timer for implementing the PWM driver. So in the IO remote driver, I use timer A1. So in PWM, I'm going to use timer A0. And the way I'm going to set this up is that the timer peripheral has something called capture and compare registers or channels. And these can be configured to trigger an output given certain conditions. And in my case, I'm going to use one of these channels to set the base period or the base frequency, which means that the counter is going to count up from 0 up to some value and then start over again and keep on doing that. And then I'm going to use the two other capture and compare registers to provide the duty cycles or the two PWM channels by configuring them to have a sub-period of the base period. And by varying the sub-period, I can basically vary the duty cycle. So for example, if the base period or the base counter counts up from 0 to 100, then I can configure the second capture and compare registers to count from 0 to 50 and to set its output to high during this 0 to 50 period, and then to set its output to low during the rest of the base period. And this means that in this case I achieve a duty cycle of 50%. The way you configure this is obviously explained in detail in the user guide or datasheet of this microcontroller. So I'm not going to go into details of the datasheet, but I think you will understand what I'm doing here when I get to the code. And I've written a long comment here on top of the implementation file to explain exactly what I'm doing. So as I said, I'm sacrificing the first capture and compare channel or register for setting the base period. And then I'm using the two other channels to provide the PWM output. And then I set the duty cycle by setting the value these capture and compare registers should count to. So for example, if I have this count value in the first capture and compare registers to provide the base period, and then I have some lower value or count value in one of the other capture and compare registers, and then the output is going to look something like this. So it's going to be high during this time, and then it's going to be low during the rest of the time. And I'm going to configure the timer to do this as the frequency of 20,000, which means that it's going to count up from 0 to this base count or base period 20,000 times per second. And I've chosen this value for two reasons mainly. First of all, to get stable DC motor behavior, you need to have a PWM output that runs at a given frequency. And usually that's going to be somewhere around 1,000 to 20,000 hertz. Because if you use a frequency lower than that, that means that you're going to switch the voltage input to the motors on and off slower than 1,000 times per second. Then the average voltage is not going to appear as an average voltage anymore, and the motor is basically going to see the voltage increase and fall, and it's going to speed up and slow down, and that's why you need a certain switching frequency. And varying this frequency can also affect the noise you hear from the motor. And the second reason I'm setting it to 20,000 in particular is because it's going to make the code a bit cleaner, because setting it to 20,000 is going to give me a base period of 100 ticks, meaning that the first capture and compare register or the base counter register is going to count from 0 to 100. And that means that I can use the value of the duty cycle, which is a value between 0 and 100, directly without doing any kind of conversion. Enough with the explanation, let's configure this timer peripheral now. First, the frequency of the timer, or how fast the timer is going to count, is going to be derived from the main clock, or the speed the microcontroller is running at. And this frequency is going to be derived from the main clock or the main subsystem clock. In a previous video I have configured my microcontroller to run at 16 MHz. So That's what this timer count frequency is going to be derived from. And I've already defined that inside defines here. Well, I have actually defined it inside UART, I think. Yeah, so let's move that to the common defines instead. Or well, I can do it like this instead. Okay, cycles. That's a bit more clear. And then going back to PWM driver, I will have this available as long as I include common defines. But similar to what I did in the last video for the IO remote, I'm going to configure the timer with an input divider, which is going to divide this input clock by 8, 3. And I'm going to go back to IO remote, and I think I'm going to move, yes, I'm going to move these two to common defines. And I'm going to rename this to input divider 3. And then inside IO remote, I have to just okay. Yes, and I'm going back to PWM driver again. And next, the base frequency, which is going to be 20,000, as I just explained, which is going to make the period ticks be PWM timer frequency hertz divided by PWM period frequency hertz. And while at it, I can also add a static assertion here just to make sure that the calculated period ticks is actually 100. And then I can do the corresponding configuration for timer 0A. First, set the clock source, which is going to be a subsystem main clock, and I select that by setting TA select 2 and then the input divider 3, and then I'm also going to set MC0, which means that the timer is by default going to be stopped, because by default there should be no PWM output. I can also add a comment here to clarify all of this. After that, I can set the period by setting the count value of the first capture and compare register. And I'm actually going to create a second define for this, which is going to be the PWM period ticks -1. And this is because the timer starts counting from 0 and not from 1. Then I should assert that the IO pins are configured as expected here. I don't need to configure them here because I already configure all of the IO configuration when the microcontroller is booted up, which I do in the IO driver. So this driver right here. And here, at least for the Ensumo, the actual robot, I already assigned the pins that are connected to the motor drivers. So in the case of the actual robot, the control pins of the motor driver is going to be connected to pin 4 and 5 of port 2, and also pin 7 as well as pin 7 of port 3. And the PWM is going to be on port 3, pin 5 and pin 6. And this exactly matches up with the schematic. As for the launchpad, I haven't actually assigned the value here yet. For the control pins, it doesn't really matter which ones I assign, since these can just be any GPIO output. But for the PWM output, I need to make sure that I select a pin that can actually mux to the timer peripheral that I'm using. And as I also said before, for the launchpad, I'm just going to connect a single motor driver, because there is no pin on the launchpad that can be muxed to the second capture and compare register of the timer peripheral, which means that I can't get the second PWM output on the launchpad. So for the launchpad, I'm going to assign pin 6 of port 1 to serve as the PWM input for the left motor driver. And then I also need to jump into my implementation file and make sure that this is configured. So I can remove that from here, and then I can move this one up to here. Just remove it from here. And with this change, the IO output, or the pin 6 of port 1, should be configured appropriately for providing a PWM output or an output from the capture and compare register of the timer peripheral. So going back to PWM, I can then assert here to make sure that it's actually configured as I expect it. So this is the configuration I expect it to have, and I can compare it by retrieving the current configuration. And then call the compare function, and with the configuration I expect it to have. And then when it's the actual robot, I can also do the same for the second PWM channel. And one thing I noticed when I wrote this code when preparing for this video is that I made a mistake inside the get current config function. So I'm going to fix that bug in this video. And the problem is that I tried to cast some of these values directly to an integer value, because I just assumed that the evaluation of this was either 0 or 1, but it's not. So I have to check whether it's 0 or some other positive value, and then set it to 1 or 0 explicitly. And also do the same for these three. Now it should work. Just remove this comment now. And this is it for the initialization of the PWM driver. So now we can move on to implementing the function for setting the duty cycle of each PWM channel. For these two channels, I'm going to create a separate struct to hold the associated configuration registers. So this register is the one that's used to set the counting mode of the mode of the capture and compare register, and this value is used to set the count value of the capture and compare register, so the duty cycle basically. And then I'm going to have an array of the PWM channels, so it's just going to be an array with 2 elements. And I'm using the same technique here as I used in the IO driver, where I take the pointer to the register variable. So similar to what I did here. And then inside this function, which should be called set duty cycle, I can first of all assert that the duty cycle is actually equal or smaller than 100, since an 8-bit integer can go above 100, to make sure that I catch it if I make a mistake here. And setting the duty cycle of each channel is going to be very easy now. Since I've set up a base counter of 100 ticks, I can set the CCR register of the corresponding capture compare register to the duty cycle % value directly. And I also have to dereference the value here. But to make this a bit more efficient, I'm also going to make sure that I disable either channel when I set a duty cycle of 0. And I'm also going to keep track of whether both of the channels are disabled, because then I should also disable the timer peripheral, just so that it doesn't keep on running and ticking unnecessarily when it doesn't have to. And that's going to save some power consumption. It's going to be negligible, but why not? So if the duty cycle is larger than 0, then it means I have to enable the channel, and otherwise I should disable the channel. So then I'm going to have a second function to enable and disable the channel. And I'm going to add a third variable to this configuration here to keep track of whether the channel is enabled or not. And by default it's going to be disabled. And to enable and disable a channel or a capture compare register, I must write to the control register. So if it's enabled, I set out mode 7, and if it's disabled, I set out mode 0. And out mode 0 basically means that this capture and compare register is turned off, and out mode 7 is what makes the capture and compare register behave in a way where it sets the output to high when the counting value is between 0 and the duty cycle, and set it to 0 the rest of the time. And there are several other out modes you can set to make the capture and compare register output they behave in different ways, and they are all explained inside the datasheet. And then I will have a function to enable and disable the entire timer peripheral. So if any channel is enabled, I should enable the timer peripheral, and if all channels are disabled, I should disable the timer peripheral. So here I can just loop over all of the channels. And if I find a channel that's enabled, that means that all channels are not disabled. And if I don't find it, that means they are all disabled. And then to enable and disable the timer peripheral, I can write to this register, and I begin by clearing the count mode bits. Similar to what I did in the IR remote when I configured the timer peripheral. And then I clear the count value, and then depending on if it's enabled or disabled, I set either MC1 or MC0. And MC0 means stop, and MC1 means count to the value in capture and compare register 0, which is where I've set the base count, the value of 100. And then I can also just add another variable here to keep track of whether PWM is enabled or not, so that I don't write to this register unnecessarily. Like that. And another thing that I'm going to do is I'm going to scale down the duty cycle, because if I run at the duty cycle of 100, with my robot, I have batteries that when they are fully charged, they're going to be at around 8 volts. And my motors are only rated at 6 volts. So if I run at a duty cycle of 100, it means that I'm going to input a higher voltage than my motors are rated for. For this reason, I'm going to scale down the duty cycle by 25%, because then 8 volts, the maximum of my batteries, is going to become 6 volts. So I multiply by 3 first, and then I divide by 4. And even though I'm using division here, it's going to be a cheap operation, since it's dividing by 4, which means that the compiler can turn this into a shift operation. And I'm also going just to make sure that this never outputs 0, because when the duty cycle percent is 1 in this case, this is going to become 0, because then this here becomes 3, and if I divide by 4, that's going to floor it down to 0, and I don't want that, since when I give a duty cycle of 0, that should turn off the PWM channel. So that's why I'm going to check if it's 1 in this case. And if it is, I'm just going to turn the duty cycle percent. And otherwise I'm doing this calculation here. Like that. And this is where I'm going to scale it. That's wrong. And since I only have one channel available on the launch pad, I'm just going to return from this function when I'm trying to set the PWM output for the right motor driver. And that's pretty much it for the entire PWM driver. So now to test it, I can write a small test function inside test.c called test PWM, and include PWM. And then initialize the PWM driver. And then I'm just going to cycle over a couple of duty cycles and measure the output with an oscilloscope, 25, 1, and 0. Then I can also wait a bit in between after I've set a duty cycle. So let's set that to 3000 milliseconds. Then I want to do this indefinitely. And then set the PWM output of the two channels, and it's only the left channel is going to have an effect when I test it on the launchpad. And then just wait. Okay, so let's see if this compiles now. It's probably not going to compile. Oh yeah, it should be launchpad. Does not. So let's just go through these errors. So why is that not found? Let's scroll up. Wait time has to be, can't be an 8-bit integer, it has to be a 16-bit integer at least. Should be suppress unused. This should be enum here. So now if I compile again, oh yeah, this should be set. Oops. bunch of errors here. Yes, this must be. I should probably try to compile a bit more often so that I don't have to fix so many errors at once. Anyway. Now it builds. I noticed one more mistake here. This should be timer A0 and not timer A1. And if I open the terminal, I should see what the duty cycle is set to at any given time. And then I can verify that it actually works by, for example, a multimeter to check the output voltage. And I'm also going to show the output on the oscilloscope to see more precisely what's going on, but let's first use the multimeter. So I'm just going to hook that up first. So now it's changing the voltage output depending on the duty cycle, and now since this is from one of the IO outputs, that's going to be, when it's fully turned on, that's at 3.3 volts, so the output voltage is going to be a value proportional to that depending on the duty cycle. And since I scale it down by 25% at the duty cycle of 100, it's not going to be at 3.3, but it's going to be at 2 point something instead. So we can see this if now. So it's at 2.4 when it's at the duty cycle of 100. And that's a duty cycle of 75, a duty cycle of 50, 25, 1, and now it's turned off. And I can also actually see it on the LED here, since that's going to change its intensity when the duty cycle changes. That's not so easy to see on this camera, but yeah, now it's turned off and now it's turned on again. So as I said before, PWM is not only something you can use for controlling the speed of a DC motor, you can also use it to vary the intensity of an LED, for example. So here you can see my measurement with the oscilloscope. It's not super clear, but as the duty cycle decreases, so does the pulse width. And you can also see the base frequency in the top left corner, that it's 20,000 Hertz. So now that I've verified that PWM works, or well, I have at least verified that one of the channels works, and then I just have to verify the next one when I move on to, or move the code to this actual robot. So since that's done now, I'm going to commit this before I move on to the next part of this video, which is going to be to implement the software layer for the motor driver. So first I'm going to create a new branch, and I'm going to call this feat motor driver, and then I can just add, or well, first I should format everything, run CPP check, and also build everything. Now I can add all of the changes. And write a commit. Then I can push this. And create a pull request. But I'm not going to merge it yet, because I'm going to keep all of the commits I'm making in this video to the same pull request. Okay, so let's now implement this part of the code, the TB6612FNG driver, the driver for the motor driver. That's going to depend on the PWM driver I just wrote, and then also set the control pins that controls the direction of the motor. So this is going to be a rather simple implementation, since like the bulk of the implementation is inside the PWM driver. So as similar to before, I'm going to create 2 files inside the driver folder. And then starting with the header file, I can define the interface first of all. And this is going to first of all have a function for initializing the driver, and then second function to set the mode, and this is going to be another enum, one value for each motor driver that I have, and then another enum for the mode. And forward is what I refer to as clockwise inside the datasheet, and reverse is counterclockwise. So basically whether the motor spins in clockwise direction or counterclockwise direction. And then I'm going to have a third function to set PWM like that. And I must not forget to also add this new implementation file to my make file. And then I can head over to the implementation file and include things. This should also have a comment on top as well as an include for stdint. And this is a driver for motor driver TB6612 FNG. And let's just do it like this now to see that things compile. Yeah. And then I can start with the initialization function. And as usual, I will have a boolean to check whether this has been called before. And then I'm going to call PWM init. And I'm also going to assert on the IO configuration, similar to how I did it in the PWM driver. I double check that I have the IO configuration, that I expect that it has been set aside my IO driver. And I expect the configuration to be GPIO output low in the beginning, and no pull up or pull down resistor. And similar to before, I can retrieve the current configuration for the different pins and assert on the comparison. And do the same for all 4 control pins. I'm just going to check the control pins of the right motor driver when I've compiled for the actual robot. And right now this assert is actually going to trigger since I haven't configured the pins on the launch pad yet. So I have to go into my IO driver and make sure that I assign some pins for the control pins of the left motor driver. And it doesn't really matter which one I pick here, but I've decided to go for pin 1 and 2 on port 2. And then inside the implementation file, I can move this. Well, again, I can make sure that this compiles. Oh yeah, I have to remove that one. And let's compile and see which one it is. And this one. This needs a return type. Missing include. Now it compiles. So then I'm going to create a struct to hold the control pins for each motor driver, just to make the code a bit more structured. And for the launch pad, I'm actually going to set the second motor driver to the same control pins as the first motor driver, just to avoid compilation error. I don't really like spreading around if defs like this, because it makes the code less readable, but you do what you gotta do. And then I can implement a function to set the mode. And here is a matter of setting the IO, the control pins to high or low, according to the datasheet of the motor driver. To set the mode stop, you set both control pins to low. For forward, you set control pin 1 to high and control pin 2 to low. And then for reverse, you do the opposite. So control pin 1 to low and control pin 2 to high. And then setting the PWM duty cycle is easy. I can just call PWM set duty cycle and cast TB to the PWM enum and just pass the duty cycle as is. And just for nitpick, I can add a static assert here to make sure that this enum matches up with the PWM enum. So this cast I'm doing here is safe. Maybe not the nicest way to go about it. And let's compile. And that's actually all there is to this implementation for the motor driver. So then I can head over to my test file and add a test function. And also include the driver I just made. And then I'm just going to loop over some different modes and duty cycles to test this. And then I have 4 different duty cycles. Then an endless while loop, and here I can loop over the different modes and duty cycles. Then the duty cycles. And then I can also make sure I test stopping them. Wait for maybe 1 second. So let's see if this compiles now. Does not. Oh yeah. And now I can test this by connecting my motor driver circuit, my DC motor and the motor driver. So just give me a moment. So now it's running at a duty cycle of 100, and you can see the motor spinning. Now it's spinning the other direction, and now it's stopped. Now it's driving forward, reversed, slower duty cycle, stopped. Yeah, so it seems to be working. Well, I should actually move this up here so that it stops in between as well, because now it was hard to see. Okay, so now it stops between each mode and duty cycle change. Yeah, everything works. So then I can go ahead and commit this change as well. So now I get a CPP check error, missing include, not sure why it's complaining. Let's just add the check config flag to get some more information. Oh yeah, this should be like this instead. So then I can go back to change that back and run CPP check again. Then it works. Build all of everything and add my changes. And then commit. And then I can push to motor driver or to the same pull request again. Okay, so I actually got the CA error on the previous commit, so let's see what that's about. I forgot to save the UART file previously, so let's fix that. I'm gonna rebase. Yeah. Then I can push again. Hopefully it will pass this time. And yeah, it passed. Okay, so now we can move on to the final software part of this video, and that's going to be to implement this drive interface here, which is part of the application layer, and I'm just going to implement this to provide a simpler interface for the application code, because interfacing directly with this motor driver, well, that's going to work. It's just going to make the application code more complicated than it has to be, because the application code is not going to need the flexibility that this motor driver currently provides. So once again, let's create 2 new files, but this time under the app folder. Or actually, I don't need to create those files because I've already created them in a previous video. So I'm just going to jump into them. And beginning with the header file, I can begin by adding a comment on top. And then I'm going to keep this drive init function, but I'm going to add 2 additional functions. One to stop everything, drive stop, and another one to set the drive speed and drive direction. And these are going to be a discrete set of directions and a discrete set of speeds. So beginning with the direction, going to have one that's just going to be driving forward or driving in reverse, and then I'm going to have one that is rotate left and rotate right and drive the arc turn. So it should be able to drive in kind of like an arc turn. So one arc turn that's going to be a very sharp arc turn, which means that the motors on the left is going to drive slower, much slower than the motors on the right. And then another arc turn that's not going to be quite as sharp. And finally, a very wide arc turn. So that's it for the different drive directions. Then I'm going to have 4 different speeds. One where it's driving slowly, and then one that's going to be somewhere in the middle, and then one that's going to be faster, and then the last one full speed. And that's it for the interface. Moving on to the implementation file, and then this is going to depend on the motor driver. And initializing this is going to be very simple, because it's just going to initialize the motor driver like that. And then for the drive stop, that's just going to set the stop mode for both motor drivers like that, and also set the PWM or the duty cycle to 0. And then setting the speed and direction is going to be a bit more complicated, because first of all I need to map the different speeds, the slow, fast and max speeds, to distinct duty cycles, and I'm going to have a big array with structs to do that. So first of all, a struct definition that defines the speed of each side. And then an array, drive speeds. And I'm going to call this primary speeds, and I will explain why in a second. And this is just basically going to be a map from drive direction to drive speeds. Okay, so if I pass the forward direction and I set the speed to slow, then I'm going to set both sides to run at a duty cycle of 25%. And similar, if it's max, I'm going to set both sides to run at the duty cycle of 100. And these are values that I've just tuned before and that I felt made sense, but I might tune this more later on. But the basic idea here is just that I map the direction along with the speed to distinct duty cycles, or distinct speeds. And to avoid having to do the same for all of the opposing directions, so to avoid having to also include drive the reverse here, since that's just going to have the same speed but be opposite to the speeds of the forward direction, I'm only going to define the primary directions here and then have a function that converts from primary direction to the other direction. You will see what I mean in a moment. So let's just define these arrays for all of the drive speeds and directions. And then I'm going to define or create a macro to get the primary direction for each direction. That's just going to be a matter of subtracting the modulo of the direction. I can actually change this to modulo 2. So a cheaper way to do modulo 2 is by just ending the value with 1, because since the modulo operation involves division on the launchpad, that's going to be a bit expensive. So I avoid that by defining a macro like this instead. So with this macro now, if I pass, for example, drive direction reverse here, that's going to give me drive direction forward. And I can actually create a assert here just to make sure that this actually works. And then I also added a comment here to explain what I'm doing inside the code. Okay, so then I can start implementing this drive set function. And the first thing I'm going to do is the primary direction. And then I'm going to get the speeds. Or the speed values. If a primary direction has not been passed, so for example if drive dir reverse has been passed, I need to actually reverse the speeds here. Primary direction. Well, let's just rename this direction instead and also do it up here. Then I'm going to have a function to inverse speeds, and I'm going to pass pointers to these. And if speed right is equal to speed right, it means that we are driving in the reverse direction, because if we are turning, the right and left speed is going to differ. And in this case I should just change the sign of the speed value. Otherwise the speed left and right differ, and that means that I should just swap the two values. It's going to create a temporary variable to hold the right speed value, and then I can set speed right to speed left and speed left. Comment swap like that. And as a sanity check, I can add an assert here to ensure that none of the speed values are 0, because there is no case where the speeds are 0 here, because if I want to set the speeds to 0, I should be calling drive stop instead. And then I can get the corresponding mode for each of the motor drivers by checking the value of the speed. If it's above 0, it means that it should be driving in the forward direction, and if it's below, it should drive in the opposite direction, counterclockwise direction. And I do the same for the other motor driver. And then I need to set the PWM duty cycle. And here I need to take the absolute of the speed value to get the corresponding duty cycle, since the speed value might be below 0 when I want the motors to drive in reverse. So I'm just going to add a define for that. So that's it for the drive code. Let's see if it compiles. Obviously it does not. And now that it compiles, let's create a test function to test this. I'm also going to initialize the IR remote here, because I want this test to take input from the IR remote to control the speed and the direction of the motors. So in each loop, I'm going to wait 1000 milliseconds or 1 second before I check if I received a command from the IR remote. And then I can check if I've received a command. So if I press button 0, I'm going to stop the motors. this, and if 1 I'm going to set speed to drive speed slow, max, and if up I'm going to set direction drive dir forward, and if down drive dir reverse, and if left drive dir left, and if right drive rotate right. And then for the rest of these I'm just going to do nothing, and then finally I can set the drive direction and the speed. Something like this should work. Let's see if it compiles. Before I flash this now, I'm going to decrease this to 100 instead to make this a bit more responsive. And then I flash this. I should be able to use my remote control to control the direction and the speed of the motor. So I can, for example, press 1 and then 2, 3, 4, and then I can change the direction by pressing down, up. Let's decrease the speed again. And now if I rotate right, it changes the direction again, then I can stop it with 0, and then it seems that it's working. Of course I haven't tested all of the code now since I only have one motor driver, so once again I will have to confirm that everything works when I move on to the robot in a later video in this video series. But for now I'm going to commit this code, or first format, pcheck, and also build, and now adding the changes, committing. And making sure that this commit also passes CI. It does. And then there is one final thing I want to do in this video while I'm fiddling with the motors, and that is to implement the last thing inside my Assert implementation, and that is to stop the motors when an Assert happens. Because usually when an Assert happens, or basically the definition of an Assert is that something unexpected has happened. And in that case, if something unexpected happens while the motors are running, I want to stop the motors to make sure that the robot doesn't just drive away and drive into a wall and damages itself. So this is more of a safety precaution when an Assert happens. So let's jump into the file where the Assert implementation is. And I already have a to-do here from before. So I'm just going to implement a function called Assert stop motors, and it's gonna be a very simple function. And I'm not going to call the drive interface here because as I've explained before, I want to make my Assert implementation as standalone as possible and not depend on any other code that potentially could have an Assert inside it and thus trigger a recursive assertion. So I'm going to write to the IO pins directly here, and going to write to both the pins on the launchpad and the SumoBot, similar to what I'm doing when I'm blinking the LED. And to make this code a bit nicer, I'm going to define a macro for setting a pin to output low. So these are all of the pins associated with the motor drivers, and I'm just setting all of them to output low so that the motor drivers are completely turned off when an Assert happens. And then I can define this macro as well. Okay, so this is just setting the corresponding registers, replacing the hashes with the port number and the pin number. And I can also use this function inside the Assert blink LED as well. So let's move this above everything and call it here as well. So let's compile and see that it works. Does not. And the reason I'm wrapping this defined macro in a do while like this, I have explained that in the coding guidelines, and that's to make the multi-statements macros behave more like functions, so that they can be followed with a semicolon without confusion. That's pretty much standard practice when writing C code, or at least good practice. So let's try this now to see that it works. We can create another test function. And then let's just trigger an assert here. And if everything works now, I should, or let's sleep here as well before I do the assertion. So maybe drive forward to 3 seconds. And then once this assert triggers, it should stop the motors and trigger a breakpoint as well as trace the assert and blink the LED. So by now it should be very easy to spot when an assert has happened. So let's build this. Flash it. Yeah, so now an assert has triggered. And I can see the LED blinking here as well. So let's now commit this as well. This also means that I'm done with the assert implementation. And pushing this as well to the same pull request. It did not pass CI, so let's see why it didn't. Oh yeah, I forgot to format the code. Damn it. Now it passed, so let's rebase and merge. That's it for the code in this video. It was nice to finally get something moving after all of these videos. Once again, I haven't tested all of this code now, since I've only tested it with one motor driver, and I will make sure to verify it later on in this video series when I move on to the actual robot, which I'm going to be doing soon. But there are at least 2 more videos I have to make before I do that, and that's going to be to write the drivers for the sensors, the line detectors and the range sensors. And another thing I can mention here is that right now I'm changing the direction and the speed of the motors quite abruptly. So for example, if the motors are driving at full speed and I change the direction, it's going to drive in the opposite direction with full speed, and that works. And in this case the motors are quite weak, so that it doesn't really matter, I think, but could consider adding some code that ramps down the speed instead of changing it so abruptly, to maybe reduce the stress on the motors as well as on the motor drivers. But I don't think I'm going to do that for this project, but it's something you can consider if you're working with motors yourself. But that's it for this video. Thanks for watching and see you in the next one.